So today I want to do a bunch of things involving essentially the next section of the course, which if you look in your textbook actually skips the electrochemistry portion of the course. So what we're moving into is electromagnetic radiation first, and then in this section of the course we'll go back to electrochemistry, and then the last section of the course will involve separations and different types of chromatography. All right, so, and that's how it's set up. So essentially, if we're going to talk about spectroscopy, we want to review a little bit about electromagnetic radiation and light. A lot of this is covered in Gen Chem 1, so I'm not going to spend huge amounts of time on it, but I do want to review a few basic things. Essentially, if we classify energy as electromagnetic energy, essentially what it means is it travels through a vacuum at 3 × 10⁸ meters per second. It has a wave-like component to it, or it actually travels in a wave pattern. But there are all kinds of different types of electromagnetic radiation. They all also travel in packets of energy, which we refer to as photons, and that's straight out of Chem 1. The reason we know that electromagnetic radiation has wave properties is because if you take what we can see, which is a small portion of the electromagnetic spectrum, and you pass it through something that diffracts, it'll bend the light. And so if you pass visible light through a prism or a diffraction grating, what happens is the wave or the beam is bent depending on the wavelength of light that's passing through my refracting medium. And so what happens with visible light is it's broken into the spectrum. And so essentially what you can think about is your eyes are detectors. They're tuned basically to detect this range of the electromagnetic spectrum. There's a much larger range outside, but your eyes are tuned to detect this. And so we can define certain facets of electromagnetic radiation, and one of them is the wavelength. Because of diffraction and because of the way diffraction gratings work, it's pretty easy to calculate the wavelength of visible light passing through the diffraction grating. And actually, you can translate that to non-visible electromagnetic radiation as well. But the wavelength is technically defined as the distance between the crest or the crests of 2 adjacent waves, although you could define it where the wave pattern crosses the origin or the distance between 2 troughs. They're all going to be the same. And we use the Greek letter lambda to denote wavelength. So whenever you see white lambda, you assume we're talking about a wavelength of electromagnetic radiation. Now, the other thing that's harder to define, but is just as important, is frequency. And essentially what frequency measures is the number of oscillations that a photon goes through as it travels for 1 second. So essentially what you can think about is the speed of light we've already defined as being 3 × 10⁸ meters per second. And so essentially what we're saying is how many oscillations does a photon go through to travel this distance? That's what we define as frequency. And so we often denote that in reciprocal seconds. So a lot of times we talk about the frequency of photons in hertz, but the easiest way to think about that is this way. The units are per second. How many oscillations per second, technically? And so if that's true, and then there's also wave number. Do you recognize the significance of wave number, having taken organic chemistry? Have you seen? Ah, okay.
I never really got that wave number.
It's in the context of infrared spectra. For some reason, organic chemists use wave numbers for infrared spectra, okay? And so essentially what you can think about here is wave number is essentially oscillations per distance. So if you have wave numbers in reciprocal centimeters, it's how many oscillations you have in a centimeter. All right. So here's what we know is true. If you multiply the wavelength in meters by the frequency in reciprocal seconds, for any photon, you get the speed of light because the speed of light is a constant. And so if you know the wavelength, you can calculate the frequency. If you know the frequency, you can calculate the wavelength of any photon. If you want to calculate wave numbers, you just take 1 over the wavelength in centimeters. That's how it's done. And so if you have a photon with 1,000 wave numbers, which is a point in a standard infrared spectrum, that photon would have a wavelength of 0.001 meters, or actually 0.001 centimeters. And then, so it would be 1 times 10 to the, or negative 5th meters. All right. So, just a couple of quick calculations. If we have a photon just outside of the visible spectrum, what is the frequency? We have to change this number, 295 nanometers, into meters. What's the fraction of a meter that a nanometer is? Yes. So you could say this wavelength is 295 times 10 to the negative 9th meters. Or if you want to write it in standard scientific notation, you slide a decimal place over 2 points, you get 2.95 times 10 to the negative 7th meters. And so if we want to calculate the frequency, we take our constant value of the speed of light, which is 3 times 10 to the 8th meters per second, and we divide that by our wavelength in meters. You see the units cancel out correctly, which is a good sign.
1.02 times 10 to the 15.
And so, essentially what this is telling you is if a photon of this light travels 1 second, it's going to oscillate that many times. That's a lot. Okay. Now, we can also calculate wave numbers. I'm not going to bother with that right now. We can calculate wavelength. Here's a standard FM frequency, 95 megahertz.
Do we convert this to regular hertz?
Yes. So what is that going to be? That's going to be 95 times 10 to the 6th, 95 million hertz. Or really 9.5 times 10 to the 7th. And so you can say, all right, my wavelength is equal to 3 times 10 to the 8th meters per second divided by 9.5 times 10 to the 7th reciprocal seconds. And so that means your wavelength is going to come up with the units meters.
3.2.
Oh, I'm sorry, 3.2. Okay. So, standard FM radio waves have or photons of FM radio have a very long wavelength. Okay, 3.2 meters, that's almost 10 feet for this one. And so, along comes a physicist by the name of Max Planck. And what Max Planck did was he said, okay, light energy, or I should say electromagnetic radiation, is not a continuum. It is quantized. There are single photons that you can see if you look hard enough of light. It's quantized. And so each quanta has energy that's proportional to the wavelength. And this H value is what's known as Planck's constant. And that's the relationship. So according to this top relationship in the equation, the longer the wavelength, or excuse me, the larger the frequency, the larger the energy of a photon. It's inversely proportional to wavelength, which means the longer the wavelength, the lower energy the photon is. So the implication here is that photons of FM radio waves are lower in energy than the photons of visible light that our eyes pick up. And so we can also determine or calculate energy of wave number. I'm going to leave that. I'm going to leave this one as well. But here we go. 600 nanometers is in the red range. What is the energy of a photon with a wavelength of 600 nanometers of light? So what we do is we say the energy of a single photon is equal to 6.626 times 10 to the negative 34th joules times seconds times 3 times 10 to the 8th meters per second divided by our wavelength in meters. And so 600 nanometers is going to be 6 times 10 to the negative 7th meters.
When would we use the other units for H?
When is a good question. It used to be that they were used in analytical chemistry textbooks, and that's why they're on the slide, but not anymore. Okay, why do we use meters? Yes, it's the SI unit. Now, chemists for a long time rebelled against that system, and that's where the other one came from, because it's just centimeters. But we've come round, shall we say. So what is the energy of this single photon? It's not going to be a very large number.
3.31 times 10 to the negative 19.
And the units are going to be joules. So a single photon of red light does not have a lot of energy, at least when you think about it on the human scale. But let's put this into perspective. Say, for example, we have a light source that is capable of generating 1 mole of these photons. We can calculate that. We can say, all right, take the energy of a single photon, 3.31 times 10 to the negative 19th joules. And if we multiply that by Avogadro's number, oops, not joules per mole, but just per mole. What kind of answer do we get for this? Okay, 199 kilojoules. That's in the realm of reasonable energy. Okay, so if you have a red light source that's pumping out photons of this wavelength, you let it run long enough, you're going to be pumping out that much energy. Okay, we're constantly being bombarded by light energy. How do you know this is true? What happens when you go out in the sun? What do you feel? Heat, exactly. Your skin's absorbing the light radiation from the sun, and it's translating into heat. What does that mean? What's going on?
That there's, in addition to kinetic energy to the
Yeah.
sun.
Okay, so somehow the kinetic energy of the photons is being transferred to your skin, to the molecules in your skin. At least, if nothing else, they're vibrating more. Okay? And that's one of the things you want to think about. It's possible to transfer the energy. If a photon is absorbed, that means that the energy that it has is going to be absorbed by whatever takes it in. All right, so we can calculate that as well if we want to. So let's think about this in terms of the full electromagnetic spectrum. The visible light, as we know it, is somewhere right in the middle of this spectrum in terms of energy. We have low energy photons here off to the right. So the scaling is pretty much bass-backwards here. All right, so I'm going to draw kind of a line there. And what we typically refer to is that the radiation that is lower in energy than the visible spectrum is referred to as non-ionizing radiation. And over here, we have ionizing radiation. Now, what does that mean? Ah, yeah, okay. So there's something about ultraviolet and higher energy radiation that can actually cause electrons to be ejected physically from molecules, atoms, or ions. And that's why we call it ionizing radiation. And that's a danger to humans. So when you're out in the sun for long periods of time, you protect yourself from ionizing radiation. You protect yourself from the ultraviolet light that comes from the sun. You don't want to be around radiation sources because radiation sources often emit gamma rays. Although you're constantly being bombarded by these things from background radiation. But one of the things that your body does have the ability to repair minor damage done from ionizing radiation, but high exposure is difficult to repair from. And that's one of the things you want to think about. The more exposure you have, the more likely it is that your body is not going to be able to repair biological damage done from the exposure. How do you get exposed? How are you exposed to higher levels of ionizing radiation? It's going outside. Okay, actually, it's kind of debatable because there are a lot of the building materials that are used have some background radiation in them as well. And the other thing is buildings tend to trap radon, which is another source of ionizing radiation. What else? Yeah, you have X-rays, okay? Every time you have an X-ray, you're exposing yourself to excess ionizing radiation. Now, dental X-rays are fairly low level. But if you have chest x-rays routinely, you probably don't want to do it more than twice a year, because more than twice a year is going to get you above what's considered an acceptable level of exposure to ionizing radiation. Same with CAT scans. CAT scans are even worse. They expose you to lots and lots of ionizing radiation. And doctors tend to prescribe them without thinking about things like that. So, yeah, you definitely want to be careful. And there is a very clear link between high exposure to ionizing radiation and cancer, particularly different types or specific types of cancer. Okay, some of it's non-specific. When my sister contracted brain cancer, one of the things that I started doing, because she was very concerned about it, she says, "How did I get this?" And so I went and I started looking. And you know, there's been some work done on this, but not an awful lot, as it turns out. And essentially, all I could find was, okay, there are certain risk factors that increase the likelihood that you're going to get glioblastoma, but nobody actually can pinpoint the root cause. Certainly with other cancers like breast and prostate cancer in particular, there are genetic relationships, okay, that can give rise. Okay, and of course, if you live in certain places, the incidence of other cancers are higher. Okay, there are definitely pockets in this state where there are high levels of certain types of cancer, or higher than normal levels, I should say. All right, and some of that could be due to exposure to ionizing radiation or exposure to chemicals. All right, I worked at Brookhaven National Lab for 3 summers, and I was working across the street from an old reactor that was not well shielded. And it turns out that if you had worked in the vicinity of that facility for more than a year, your risk factor for certain types of cancer was higher, and there was actually a settlement. My father died of cancer, and we got money from the government out of a settlement because he worked at Brookhaven for 45 years. All right, so there are definitely things like that. But then there's this question down here. One of the things that comes up often, and I had a friend who was a statistician who was actually involved in 2 studies with this. Does the use of cell phones increase the likelihood of certain types of brain cancer?
It's like a negligible amount.
Well, it depends on who you talk to. Some people say, a friend of mine was involved in 2 studies. One study concluded that there was no correlation. The other study concluded that there was, and it had to do with how they handled the statistics. Here's what you want to think about, and this is what we're going to talk about a little bit more as we get into spectroscopy. Okay? Non-ionizing radiation clearly affects molecules. Okay? How does it affect molecules? Oftentimes vibrationally. Infrared radiation, it's proven. You hold your hand under an infrared source, it's going to get warm. Why? Because the photons that come off of that source are absorbed by the molecules in your skin. They start to vibrate more. They get more kinetic energy. Same with microwaves. That's how a microwave works. You pop something in a microwave. Essentially, the microwave is bombarding your glass of water or whatever with photons. The energy of those photons is absorbed by the water. The water molecules start to vibrate more. They heat up. Okay. What's unclear is, does that lead to biological damage? Hard to say. Okay, so if you look at the visible spectrum, violet is the highest energy photons in the visible spectrum, and red is the lowest energy. Okay, so actually 600 nanometers is in the yellow region. I said red before. All right, so here we can look at these different things, and we've already talked about that. Okay. Now here's something else we want to think about. I'm not sure how well this is going to work with this projector. Sometimes it works better than others. If I have something that appears red, say for example, I have a piece of glass that appears red. What is happening to the visible light that's passing through it?
Only the red light is getting through to you.
Okay, let's see that here. What I did was I took a red shading in PowerPoint and put it over this spectrum. Can you see the other colors in this spectrum?
Yes.
Pretty much. What I noticed though is that in this region of the spectrum, I don't see as much. All right, and so what you can interpret from this, and I also did this with blue just for the fun of it, is you can interpret that the way this works is if something appears a certain color, what it typically means is that it's absorbing the color of light that is opposite to it. Okay, so if something appears blue, the color opposite of blue is yellow. It's not so easy to see that here. But if something appears red, the color opposite of red is green, and that's easier to see on this. Okay, if you do this with colored glass, it shows up a little bit better. But here's the color wheel. I found this on the internet, and you can see the color opposite. So red, green, blue, or yellow is kind of opposite of violet and blue violet. Blue is truly the color opposite of orange, and so on and so forth. So if you have something that appears reddish, it's most likely going to absorb green light most strongly. Now what this doesn't account for though, and this is something you saw with your copper in the second lab that you did, the volumetric techniques lab, is that the copper solution appeared blue-green, which suggests that it's going to absorb strongly in the orange region. And it actually does, but it absorbs even more strongly in the infrared region, in the very near infrared region, and that's what you were picking up, because you were using 800 nanometers, which is really outside of the visible spectrum for humans. So this is basically saying the same thing. And this holds true for any type of object, whether it's visible or not. Okay, now, what gives rise to the absorbance of photons in molecules? One, electrons can be promoted from low energy to a higher energy level. Okay, in the case of ionization or ionizing radiation, what happens is electrons can actually be physically kicked out of the molecule or ion or atom that they're part of. They absorb enough energy that they just leave. They have enough energy to escape the attraction to the nucleus or nuclei.
Would that be a promotion?
Yeah, it's a promotion. It's a promotion to an infinite energy level. Okay, but at the same time, you also have promotions from one orbital type within a molecule to another. Okay, and that's what actually gives rise to the absorbance of visible photons. And that's how our eyes work. Essentially, our eyes have different compounds in them that detect photons of specific energy, and then that information is all put back together by our optic nerves and sent to the brain. Or actually, the answer, I should rephrase that. The energy or the information is transmitted to the brain via the optic nerves, and then the brain puts it together. It's very complex. You know, every time you perceive something, essentially, your brain is doing massive amounts of work. And what's interesting, too, is that your perception can change. When my sister had her surgery after her diagnosis, her vision was double. Something had changed. And the doctor, and we went to the doctor and we said, oh, the vision's double. What are we going to do about it? And he says, oh, it'll fix itself over time. Sure enough, she woke up one morning, it was gone. The reason it was gone is not because anything had changed physically in her brain, but her brain adapted to the new circumstances and basically took that information and interpreted it a different way. Another way you can see this is if you put a pair of glasses on somebody that flips images over, after about the third or fourth day, that person will wake up and see things right side up again.
So if they took the glasses off,
Then they'd see things inverted again, and then another 3 days go, the image gets turned right back over. So your brain adapts to things, especially after it has learned how to perceive certain things to begin with. Okay, so higher energy photons are definitely going to affect electrons. And the absorbance of high energy photons can definitely cause electrons to be promoted to higher energy levels, or in extreme cases, kicked out. All right. Lower energy photons tend to affect vibrations within molecules. If you think about a bond being a spring, it causes the bond to move back and forth. It causes the bond to wiggle. Okay, it can cause other vibrational transitions. And then also, we find with low energy photons that if you put a nucleus or an electron into a magnetic field, the absorbance of a photon can cause the spin of the nucleus or electron to flip. So high energy photons will cause electronic transitions. Moderate energy photons, lower in energy than visible photons, cause vibrational transitions, and low energy photons can also cause spin transitions in electrons, nuclei, neutrons, things like that. If you've seen NMR, that's the basis of NMR. Okay, in an NMR, you have a magnetic field. And basically you place your sample in the magnetic field. All the nuclei or nuclear spins either align with the magnetic field or against it. You pulse with the right frequency of photons, they flip. All right, so one thing that happens as a result of this is that if you have compounds or ions or atoms where allowed transitions are of appropriate energy, those atoms or ions are going to absorb photons of very specific energies. They're not going to absorb photons that don't have those energies. And so that's why you see things as being colored. And that's how you detect things as well in different types of spectroscopy. In infrared, you know that there's a vibrational band for carbonyl groups at around 1600 wave numbers. And the reason you know that is because that vibrational transition requires the amount of energy that those photons generate when they're absorbed. And so, if all you had to think about was promotion from one energy level to the next, if you were measuring the visible spectrum, say of nickel or something like that, what you would expect to see are very sharp absorbances. Is that what we see in visible spectra? Is that what we saw in the copper-2 spectrum that we measured in the lab, or with the cobalt-2 spectrum? Do you see sharp transitions? No. Okay, so there's something more going on. And here's what you have to think about. You have to account for vibrational transitions along with the electronic transitions. And so what that tends to do is it tends to muddy things out. So instead of seeing two sharp peaks in an absorbance spectrum, you're more likely to see something like this, where the peak is spread out, or there may be actually two actual electronic absorbances underneath there, but they're spread out by the vibrational transitions. And so that's one of the things you have to think about. If you can single out atoms, if you can atomize a sample, then you can eliminate those vibrational transitions. That's the only way you can do it. If you have molecules, you can't eliminate those vibrational transitions. So you tend to see broadening of things. All right, that's one set of slides down. Let's move on to the next set. What we want to do is we want to lay some groundwork for spectroscopy, and then probably after the exam, we'll pick up and we'll talk about specific types of spectroscopy. Atomic absorption, UV visible. Oh, that reminds me. Next week in lab, 2 of you are going to have to do atomic absorption, and 2 of you are going to have to do UV visible spectroscopy of iron. What are your choices? You guys have free reign since you're the only ones here. Would you rather do spectrophotometric determination of iron phenanthroline, or would you rather do atomic absorption of a copper in a plant nutrient? They both.
The atomic absorption
Yeah.
yeah,
Okay. All right. So that means John and Noah are going to have to do. They're going to have to do. What I'm going to say right now is Noah's going to work with Ben on atomic absorption, and John will do spectrophotometric determination. Okay. Actually, and the reason we do this is because we only have one AA spectrometer. All right. Now, we're gonna jump forward a little bit, and the reason I do this is because I want to lay some foundational work for what you are going to be doing next week in lab, whether it be the iron phenanthroline or the atomic absorption lab, both the same sort of thing. We've talked about linear relationships before. You actually generated a linear graph in one of the labs you did following Beer's law. You're probably not going to get to Beer's law today. We'll see. Anyway, typical linear relationship. Y equals mx plus b. Slope is defined as change in y over change in x, and b is the intercept. Now, what we want to do here is we just want to look at how Excel deals with this. Say, for example, you generate 2 different data sets, and you want to say, well, which one represents a straighter line? The one on the left or the one on the right? What do you think? Kind of hard to tell, isn't it? Yeah, I would be inclined to as well, although there's curvature to this one that doesn't exist in the other one. The other one looks like it's just natural scattering. So how do we evaluate this? How can we use some statistics to decide which of these would give us better straight line data? Okay, how do you do that? That's what this is all about. You plug it into Excel, right? And you let Excel do the work, which is nice and convenient. But here's the root behind it, all right? You can calculate your average x value and your average y value just by summing them up and dividing by the number of points. The slope is calculated in this fashion. And the intercept is calculated like this. So this is how Excel does it. It takes all this information. In the bad old days, you had to do this by hand. My father used to tell me stories of doing this with a slide rule by hand. And you know, it's a lot more tedious. It takes a lot more time than what you're used to here. But the other thing that Excel spits out, which is really important, or I should also say LibreOffice Calc will spit this out, is an R-squared value. So if you take a set of data, you plug it into Excel or into LibreOffice Calc, and you do your linear regression, okay? In other words, you add that trend line, you say the trend line is linear, you have Excel or Calc match that trend line to your points. You always want to display the equation, and you always want to display the R-squared. Because the R-squared value gives you a statistical indicator of how well your points match to a straight line. Now, one other option you have with Excel is that you can force your trend line through the origin, through 0, 0. And that depends on the circumstances that you're using. What we're going to do is we're going to look at two different types of analyses involving trend lines and involving this method of least squares. One is you just make a set of standards and then you match an unknown versus the calibration curve, as it were, from your standards. Beer's law. You've done Beer's law. The second is what's called method of standard additions, which we've talked about very briefly, but I want to talk about in much more detail because here it has tremendous relevance. Okay, I'm going to skip the quality assurance business. So let's talk about these standardizing methods of instruments. All right, and there are two that we use. If you're doing the iron phenanthroline lab, of course both of you will eventually do it, you're going to make up a stock solution and then you're going to make up a bunch of serial dilutions. If you think back to the volumetric techniques lab that you did, what was that, 2 weeks ago now? Same thing. You made up a stock solution, then you took that stock solution and you made a bunch of serial dilutions with it. Okay, that's basically it. And you've done this before if you've taken Gen Chem 1 or Gen Chem 2 lab here. In Gen Chem 2 lab, the equilibrium constant lab is tied to serial dilutions. You make up a bunch of serial dilutions of the iron thiocyanate complex to calibrate your, or to make a calibration curve, and then you determine equilibrium concentrations of that same complex in other mixtures from that calibration curve. In Gen Chem 1, you made a calibration curve of cobalt solutions, and then you determine the molarity of cobalt in an unknown. All the same thing. The second one is a little bit more complex, but it actually is very useful. In some cases, it's better to use what's called standard additions rather than serial dilutions because of the way the solutions are set up. There's a student right now who's interested in testing water for lead. You know, he's been reading the news lately, and of course there's been a lot of controversy over the Newark water system, and before that, the Flint, Michigan water system. And the sad truth is that at least Newark is trying to do something about their problems. Flint, Michigan, the problems have been going on. Nobody's had the political will to do anything about it. So in a case of of standard additions, what you're going to do is you're going to take a fixed amount of your unknown, put that same amount into a series of solutions. And then what you're going to do is you're going to spike some of those solutions with known amounts of the same component. And so what happens in that case is instead of getting a straight line that goes through the origin, you're going to plot instrument response versus how much of the known you've added. So we could say amount of known. And because this is true, oftentimes the first point you get, even though you've added 0 known amount, you're going to get some instrument response. And then each time you add more known, the instrument response goes up. Assuming there's a linear relationship between instrument response and amount of the ion or compound in solution that you're looking at, you can get a straight line, and you can extrapolate that straight line back to where it crosses the x-axis. And that point is going to represent the concentration of, or really, I should say the negative concentration of what was in the solution before any known was added. And the easiest way to calculate that is you just divide the intercept by the slope from your linear data. So in the atomic absorption lab, you're actually going to do both methods. You're going to make up a serial dilution set of solutions, and you're going to make up a standard addition set of solutions. And you're going to test them both and see what they tell you. See if they give you the same data. Okay, now internal standards we can say is essentially the same thing as serial, or excuse me, as standard additions. All right. One of the things you also want to do is when you're doing spectroscopy of any sort, you have to have some kind of blank. If you think about UV visible spectroscopy, what's the first thing you always do? You take a cuvette with a blank solution, usually just water, pop it into the instrument, and you zero the instrument out on that blank. There are other situations, though, where blanking is going to involve something else. If you think, for example, if you think back to the iron thiocyanate complex lab, you made up a blank that contained iron 3 because iron 3 might have a small amount of absorption associated with it. And you use that blank. Okay, the other thing is if you're going to do massive quantities of spectroscopy, you want to introduce controls periodically to test to make sure everything is working correctly. And so if you're working in a pharmaceutical lab, you're working for any company that produces chemicals that practices good quality assurance, what they're going to do is you're going to go in, you're going to run these different techniques, but periodically what they're going to do is feed a control into the stream just to make sure that you get reasonable values for those controls. It's a way of validating the method. Okay, so let's look at some information. Here's a serial dilutions problem. Okay, this, you could almost call this Beer's law, if you will. I've got a certain amount of protein that I add to a solution, and I measure the instrument response based on those concentrations. And essentially what I want to do is I want to say, all right, I have an unknown that gives me an instrument response of 0.2. What is the concentration, or how many micrograms of protein are in that unknown? What am I going to do? I am going to make a standard plot. I'm going to plot instrument response on the y-axis because it's the dependent variable, concentration or amount of protein on the x-axis. That is the independent variable. And there we have it. So this is something in preparation for not the exam next week, but the following exam. You might want to go back and look at some of these examples and try them on your own. What does this look like? Does this look like a truly linear response?
I wouldn't say truly linear.
No. It actually looks to me like there might be some curvature to it, and sometimes you see this. This is another thing you want to think about. You do Beer's law, assuming Beer's law holds, but does it hold all the time? Okay, so one of the ways we can tell the linearity or lack of linearity is by looking at the R-squared value. In this case, it's kind of on the edge. Of course, the closer that R-squared value is to 1, the more linear my data. And you have the visual confirmation of that. You've got a couple of points that appear to be outliers. Now, what would you do if you wanted to try to rectify that situation? Well, the easiest thing to do is to go back and measure those 2 points again, just to see if there's a difference. All right, and that's another thing you want to think about. There is going to be some natural variability in instrument response. One potential source of that is the fact that your solution is not completely mixed. But another potential source of that is going to come down to the instrument itself. So what you could say is, all right, I measured this once. Maybe I should measure it a couple of times and take the average. And that's one of the reasons we do that. You always do 2 measurements of each and take the average, because the response does vary, and it varies naturally. It may not have anything to do with the fact that you didn't mix up your solutions. It just is something that happens. Okay. So now here's the other question. If I have a solution that has a response, or I have a sample that has a response of 0.2, how could I find the mass of the protein in that sample? And I made a blunder here as well. Except that's not right. My dependent variable is on my y-axis, and so this is going to be instrument response. On my x-axis is going to be milligram or micrograms of protein.
So you just look at 0.2 and go to the right.
Okay, so that's one way we could do this. We could say, all right, my instrument response is 0.2. I could go and then go down and check. So from that, it looks like about 12.5 micrograms, right? What's another more precise way to do that?
Calculate the slope.
Yeah, and that's why we do this. We've got the slope, okay? In this particular case, the graph tells me that the slope is 0.016. Exactly. So you can use y equals mx plus b. Now b, what is the value of b? What is that value in this graph?
0.
Yeah. I force this line through 0. And that's typically what you want to do with Beer's law plots of any sort. You force that line through 0.
How would you do that?
Oh, you just tick a box in Excel and it does it. Okay. There are 3 boxes. You always want to tick show equation, show r squared, but the first one is set intercept equal to, and you just tick that and leave it at 0 and you're good to go. So another way we could determine this is we could say, all right, if my response is 0.2, I can divide that 0.2 by the slope. And that will give me my quantity. And that's going to be moderately more precise because it's just easier to see, or it's easier to do. So it comes out exactly the same. That's good. That means we visualized things pretty well. All right. So here's another one, same sort of thing. I'm going to leave this for you to do, but you can look at this later on. You can do exactly the same thing. You figure out your response, and again, you see, in this case, there's even more deviation from linearity than there was in the previous example. Now, what I want to do is I want to move on to standard additions, because this is really important, and this is stuff you haven't really seen before. Here we've got a bunch of samples that contain, or we have a sample that contains lithium. It's in an unknown solution. What we're going to do is we're going to spike quantities of that unknown solution with a standard and then dilute to a new volume. And this is a typical standard addition setup. What's hard about this for most students is figuring out how, or what's really happening here. And I've been racking my brains about this for a long time. In this particular case, we have an unknown solution that contains lithium. very low quantities of lithium, apparently. We also have a standard solution with a known concentration of lithium of 0.00162 parts per million, which would be 1.62 parts per billion. It's a very low concentration. And so what happens here is we make up a series of diluted solutions. Now, the part that's difficult to understand is the reason this is done is because you want to make sure your instrument response is within a reasonable range. And that varies from instrument to instrument. Okay, apparently in this particular case, at least we want to keep it looks like we want to keep the instrument response below 1,000 for whatever reason. Okay, if you're doing absorbance measurements, your best bet is to keep absorbances below about 0.8 or 0.9, or in extreme examples, 1, and I'll explain that later on. And so one of the things that you'll notice is both with the AA lab and with the iron phenanthroline lab, you have essentially canned concentrations. We've done this lab so many times in both cases that we know what those concentrations are and we tell you. But if you're developing a new method, this is something you have to think about. How do you know what to look for? Okay, well, you look at protocols. For example, with atomic absorption, you say, all right, I want to do studies on copper. One of the best ways to find information about AA is through the Environmental Protection Agency. They have a document that's about 30 years old that's readily available online. You can download it. You have to wade through lots and lots of things, but you can find their recommended parameters for copper. How do you set the instrument up? What is the parts per million range that is reasonable using that setup? That's what you want to think about. So apparently here, whatever the parts per million that we end up with seems to work for this. But notice also, you have an instrument response even though there's no added lithium to the solution. Okay, so now we figured that out. Now we have to figure out our dilutions. And this is where I'm experimenting a little bit. We can kind of map this out. And this is useful. Each of our 5 solutions that we measure the instrument response for has 10 milliliters of the unknown solution in it. But we also are we're spiking some of those samples with this 0.00162 part per million lithium sample. The thing you want to think about too is we're not doing all of them. And we're also diluting these things. So we put 10 milliliters of the unknown in. We also put a certain quantity of the lithium in there. Whatever instrument response we're going to get is for this 100 milliliter solution. So we're going to have to work back from that to get the concentration of lithium in the unknown. But the first thing we can do is say, all right, if we add these volumes of our 0.00162 part per million lithium sample to our unknown and dilute it, what will be the new concentrations of added lithium in there? Now, of course, in the first case, that concentration is going to be 0.000 parts per million. How do we get these other concentrations? If we add 5 milliliters of a 0.00162 part per million solution and dilute that to a total volume of 100 milliliters, what's the new concentration of added lithium in that solution? What's the equation we use? Remember, especially in really low concentrations, we can define parts per million as milligrams per liter. And so, for this first solution, we're going to take 5 milliliters. We're going to multiply that by the concentration of lithium in that solution. And then we're going to divide that by the total volume of the diluted solution. So essentially, it's a 20-fold dilution. So if I do my math correctly, and let's see if I can remember this, it's 0.00081. Is that correct?
There's a
So
fourth zero.
fourth zero?
Yeah, there's a zero. It's 0.0000081.
Really? Okay. Yeah, you're right. Sorry. You're absolutely right. Okay, so what you might think about with this is you could change it to parts per billion and have more manageable numbers if you wanted to. Okay, so what's the next one going to be then? It's going to be 1/10, so it's going to be 0.000162. Next one, 0.000243. And the last one, 0.000324. Okay, so now what I can do is I can plot concentration of instrument response, because I want that on the y-axis, versus concentration of added lithium. And so what I did on the next slide is I essentially took that data, put it into a spreadsheet so that it'll read straight out of Excel. X data first, Y data second, and I make a plot. So now, how do I calculate the ppm of unknown lithium in these 100 milliliter solutions?
You take the intercept and divide it by the slope.
Yeah, so we're going to take the intercept, which is 305. And we're going to divide that by 2 times 10 to the 6th. That doesn't sound right, does it? That's going to give me a huge number. I think it's the other way around. Let's try that.
Zero.
So what?
The denominator is actually huge.
Yeah, the denominator. Oh, I'm sorry. You're right. Yeah. Okay. So 0.00, at least.
Yeah, this is the third zero, then it's 153.
Okay. 0.000153 ppm. Okay. That's what's in the 100 milliliters of solution. Now, let's think back. How do we make that? So according to this, oops, I've got that wrong. There's a third zero in there. This is our amount of lithium from the unknown. What's the concentration of lithium in the known? Or, excuse me, in the actual unknown solution? What did we do? we have that concentration of lithium. How do we make that solution? We took 10 milliliters of the original solution, except I've got this backwards. What am I doing wrong? How do I go the reverse direction with dilutions? How do I get the concentration of a more concentrated solution? I'm going to do this. Because I took 10 milliliters of that concentrated, or that more concentrated solution, I diluted it to 100. So this is the concentration of my lithium in the 100 milliliter solution. That came from 10 milliliters of the stock. And so that means the concentration of lithium ion in the stock is 0.00153 parts per million. This is the problem with this stuff is it's really hard to track what's going on. This is one of the easier ones. In the copper lab, in the AA lab, you're going to do, I think, a twofold dilution before you get to this point. You're going to weigh out some of the nutrient. You're going to make a concentrated solution of that, and then you're going to dilute it once and then again, if I recall. So you have to track those dilutions when you do this. No. Okay, so let's do another one from scratch. We have a certain element X. It's not specified what that is. Aliquotes of the unknown solution were mixed with aliquotes of the standard. Aliquote, you could say parts, if you want a synonym that makes more sense. Okay, this is a word that's often used, and what it implies is that you're pulling volumes of the solution out with a pipette. Okay, so in this particular case, we're also adding 10 milliliters of the unknown to each solution. And then we're adding 1, 2, 3, 4 milliliters of the known, and we're diluting again to 100 milliliters. So we can map that out. And again, I'm going to do this one by hand, which means, of course, it's going to look pretty lousy. Okay, so here's my unknown. In each case, I'm going to make 5 solutions. And to each of those solutions, I'm going to add ten milliliters of my unknown. Now, what else am I doing? Down here, I have a 1.000 part per million solution of X. Oh, and I should also write here, what are the volumes of these solutions? The total volume of each of these solutions, according to the problem, is 100 milliliters. And so, to the first solution, I'm adding 0 milliliters. The second solution, I'm adding 1 milliliter. Third, 2 milliliters. Fourth, 3 milliliters. And fifth, 4 milliliters. And so, in each of these diluted solutions, what's the concentration of added X? What is it going to be in the leftmost one? Yeah. First one. Take a 1 part per million, or take 1 milliliter of a 1 part per million, dilute it to 100. That's a 100-fold dilution, so that means we're now going to have a concentration of 0.010. Okay? We know the concentrations. We also have the instrument responses measured. And so what we can do is set up another spreadsheet. And actually, what you can do is you can set this all up in one spreadsheet if you want to. It's pretty easy to do. Okay, you can just translate the data over. You can say, all right, I want on my x-axis, I could set up a column here and say, all right, I'm just going to translate my instrument response over 2 columns. So I could set up here ppm added x, and then I can translate over my response. And so I just copy these values over into this column, and then I can just set up a calculation. That cell times the concentration divided by the total volume of the diluted solution, which is 100 in this case. And so you can just set up your spreadsheet, spit out those numbers. I did that on a separate spreadsheet, but you don't have to do that if you don't want to. I just did it to make things clearer. And there I have it. And there's my plot. So what does this tell me the concentration of X is in my diluted solutions? And you can think about this too. How do the units work out? The slopes of these lines is going to be reciprocal concentration unit. So technically, the slope of this line is going to have the units reciprocal parts per million. And essentially what it is saying is if you had a 1 part per million solution, that would be the instrument response that you read. You've seen that with Beer's law as well. So 0.162 divided by 8.02, what do we get?
0.02.
0.020?
Yes.
Okay. So then, if that's true, what is the concentration of lithium in the unknown? Here's what you can think about. To make these solutions, which we know are 0.020 parts per million, we took 10 milliliters of the known, screwing this up again. I had 100 milliliters of that solution, but I made that solution by taking 10 milliliters of the known, or of the unknown. And so here, this is going to translate into 10 times as much, which means this solution has a concentration of 0.2 parts per million of X. So these are definitely ones that you want to get comfortable with doing. Of course, that's part of the reason for doing the lab, and we will look at other examples as well. But the method of standard additions is commonly done, and you'll definitely see it in this course and perhaps down the line. All right. that's it. Yes. All right, so last thing we want to do, how much time do we have? Okay, we got enough time, at least to start this, is we want to look at visible spectroscopy next. So we talked about things in kind of general terms. Now let's talk about some more specifics. And one of the specifics we're going to get into is the derivation of what absorbance is, which is what both of you will be reading off of the instruments in next week's lab. Okay, so in general, you've used UV visible spectroscopy, but we haven't really talked about what it does. Okay, two purposes. The main purpose that we're interested in is that we can determine amounts of a whole bunch of different analytes quantitatively. You've done this before. Anything that has color, the intensity of the color has a linear relationship to the concentration of whatever gives rise to that color. But you can also do it with components that absorb ultraviolet light instead. For example, we have a lab, and this is a potential independent project for one person later in the semester, where you take aspirin and you do analysis of aspirin using ultraviolet spectroscopy instead of visible. So you make up a bunch of standards of the component of aspirin, and you make a standard curve, and then you tie that back to how much aspirin is in a tablet. Okay, so you can do that. And we also use this as detection for certain types of chromatography like HPLC. The other thing that we can do with this, although it's not very commonly done anymore, is you can identify organic functional groups by UV spectroscopy. Anything that has a pi bond in it is going to absorb quite strongly in the ultraviolet region. And depending on where that absorption is, you can tell what the functional group is. It's not very precise, though. That's the problem. And that's an issue that we run into. So that's one of the reasons why it's fallen out of favor. So in this case, the sample size is going to be variable. What you need, though, is you need to have a sample that will allow at least some light to go through. So what's the most common way we make up samples for UV visible studies? How have you done it in the past? Yeah, you make up a solution of some sort. You have a solvent that essentially is transparent, and you dissolve some of your analyte into that solvent. But again, you have to gauge it so that enough light passes through that the instrument response is decent. Okay. The other thing is you want the container of your sample is in to be transparent. This is a problem if you're going to be doing ultraviolet spectroscopy. If you use glass or plastic in ultraviolet spectroscopy, the containers are no longer transparent. And this is something, where do I have that? Somewhere in here I have a slide on choose your material wisely. Okay, the standard setup for any of this type of thing, and this is also true for atomic absorption, is you have some kind of light source, you have some kind of device that isolates a specific wavelength from that light source. The light source is often just a tungsten light bulb, because tungsten light bulbs generate a pretty even spectrum of visible light. On the other hand, LEDs are not good that way. If you look at LEDs through spectroscopes, you will see gaps in the visible spectrum. They appear to cover the whole spectrum when you just look at them with the naked eye, but if you have some kind of diffraction grating, you'll see that there are gaps. So we often use tungsten, which is an old school light. You have some kind of sample compartment. Okay, it's a cell that's made of glass or plastic or quartz in some cases, and then you have some kind of detector. Now, one of the students last year we came up with a very interesting project for him, and actually this is something that could be built on. We actually built a very simple spectrophotometer using LEDs and a voltmeter. We used a specific wavelength LED as a light source. We used another LED as a detector, because if you hit an LED with light, the LED will actually generate voltage if there's no current going through it in the first place. And so what this guy did is I actually 3D printed him a case for a spectrophotometer. I soldered it together for him with a light source and an LED detector in it. And then I hooked up the 2 poles of the detector to 2 plugs. And you could just plug a voltmeter straight in there and measure the instrument response from that. And what we wanted to see was, well, does this crude spectrophotometer give us roughly the same precision of data as a working spectrophotometer? And so he tried this with cobalt solutions. You could try it with some other solutions as well. The other thing that would be interesting to do with this device is to come up with some kind of script using an Arduino or a Raspberry Pi or something like that, that takes the output and basically makes it into something that's usable. It'd be pretty simple to do, but that'd be an interesting project for somebody. Okay, so the light source has to have basically a full spectrum of whatever you're using. So for visible, we use tungsten. For UV, we use a deuterium lamp. And these are kind of expensive, but we've got a few of them around, and they work. The other thing that happens is if we happen to have an instrument that has, or that is capable of measuring both, which we do, then we have to have both types of sources in there, and the instrument has to have a way of switching back and forth between the 2 sources at a certain point in the spectrum. The wavelength isolation device is some kind of mirror or prism or diffraction grating, depending on what it is. And it's often used in conjunction with a narrow split. In other words, the beam of light that actually passes through the sample is usually about 1 millimeter or 2 wide or less. Okay. Sample compartment, it just holds the sample. Now, there are 2 different types of spectrophotometers. The types that we have currently in the lab are all single beam instruments. And the way these work is you put a blank in, you read the blank. Every other thing that you read has subtracted whatever the response is from that blank out first. And so in order to use a single beam instrument, in other words, you have to have some form of crude computer. And all of those spectrophotometers have a microprocessor in them. And the microprocessor is programmed to do all these things. In the bad old days, we didn't have this capability. Instead, what we had to use was called a double beam instrument. The double beam instrument subtracts the blank out in real time as opposed to from the beginning. And so double beam instruments tend to be mechanical. The last double beam instrument we had was an infrared spectrophotometer, and we got rid of it about 3 or 4 years ago because it quit working. It was just too old. But when I was an undergrad, double beam instruments were the norm because computers in those days were so much more expensive. I mean, now you can do all kinds of fancy calculations on a $35 computer, a Raspberry Pi. Okay, the detectors are often photomultiplier tubes, although another type of detector, and this is how an LED works as well, is diode array. You have an array of LEDs essentially, and as light hits those LEDs, they generate voltage. And so then what you have to do is somehow pass that data through a computer. In a standard spectrophotometer and actually in a diode array as well, the raw output is voltage. If you have a actually, I'm sorry, no, that's not true. For a photomultiplier tube, the output is current. The number of electrons hitting the photomultiplier tube affects the current that it generates. But for a diode, it's voltage. And so what you have to do, of course, is take the output and feed it into a computer of some sort. All right, so here's kind of a standard thing. You've got a lot of fancy optics in here, and that's one of the things you have to be aware of, is these instruments are delicate. Now, a diode array is really interesting because in a standard instrument, what you have to do is you have to scan through the series of wavelengths. And so collecting a spectrum can take several minutes. Actually, it used to be much longer. Sometimes I remember doing spectra that would take 15 minutes to collect. With a diode array, what happens is you pass a beam of polychromatic light through your sample. Then the light is broken up, and the diffraction grating aims specific wavelengths at specific diodes. And so what you get from a diode array spectrophotometer is you get a full spectrum response in a matter of less than a second. We actually have a detector on our HPLC, or one of our HPLCs, that will generate a full UV spectrum for every fraction that comes off of the HPLC. And so this is a very powerful technique. All right, here's what I was talking about before. I measured absorbance spectra of 3 different materials using an old spectrophotometer that we have. For glass and for polystyrene, you can see the cutoffs on these spectra. Okay, for glass, really anything above 290 seems to work okay, but you go below 290, you're getting all this wavering in there. That's clipping. The detector, there's so much absorbance that the detector is really not capable of picking it up. Polystyrene goes down to about 270 nanometers or so. So polystyrene would be a little bit better. But if you want to study things that have activity in ultraviolet, you want to use pure silicon dioxide. Now, it looks like there's a strong absorbance down here at 200 nanometers, but look at the scale. Here the scale is 4 for these two, and here it's 0.2. So that's low enough that if you blank with your quartz, it will be subtracted out, even though there is some absorbance down there. And you can also see with quartz, there is some slight absorbance in some of these higher wavelengths. But again, if you blank with the same quartz tube, you're just going to subtract it out. And you always should use the same container for all UV visible measurements. So you pick a cuvette, you stick with it until you're done with that day's work. Because if you blank on a different cuvette, it's not going to work. All right. Now, technically, what happens is when you measure any absorbance, you're not getting absorbance directly. What you're getting is some kind of power, whether it be voltage, whether it be current. Now, what you're going to do is you're going to measure 2 samples. You're going to measure a blank, and then you're going to measure what you're trying to analyze. The power that your analyte solution generates is going to be less than the power of the blank. So you can write that down. You can always say this. P is less than P0. Now, we can calculate transmittance by just taking the ratio of the two. So T, by this definition, is always going to be not less than 0. It's going to be less than 1. But oftentimes what we do is we take that T and we multiply it by 100, and we get percent transmittance. If you think back to Gen Chem 1 lab, if you took it here, that's the root of this equation, which was given in the Gen Chem 1 lab manual. I know it because I wrote it. Okay, now the other thing that's true here is the definition of absorbance is not log of P over P0, it's negative log of P over P0, because that log term would be negative. Okay, technically what absorbance is either the log of 1 minus the log of your transmittance, or the way it's shown in your your Gen Chem 2 or your Gen Chem 1 lab manual is it's the log of 100 minus the log of your percent transmittance. Log of 100 is 2. That's where that 2 comes from. Now, the other thing you should be aware of are these two terms at the bottom. If we're dealing with a solution where the concentrations of analytes are in parts per million or parts per billion, we often report an absorptivity value. And essentially what an absorptivity value is what would the absorbance be of a solution of that analyte with a concentration of 1, whatever unit you have. 1 part per million. How much absorbance, or what absorbance value would a 1 part per million solution have? What absorbance value would a 1 part per billion solution have? Okay, and so absorptivities have reciprocal concentration units. If we're dealing with molar solutions whose concentrations are in moles per liter, we report that absorptivity as molar absorptivity, and we give it a different name. And essentially what it says is if you calculate a molar absorptivity, it's the absorbance that a 1 molar solution would have. So the first thing you probably did if you took chemistry here is you did this with cobalt-2 ion in solution. And the typical value absorption constants that you get for cobalt-2 are in the range of 5.2 to 5.4 per mole, or per molar. That means if you were to have a 1 molar solution of cobalt-2, the absorbance would be 5. There are other analytes, like that copper acetate you were using 3 weeks ago, or 2 weeks ago, that have molar absorptivities in the hundreds. There are other compounds that have molar absorptivities in the thousands. Okay, the iron phenanthroline complex fits that bill. Okay, you're actually going to be using part per million concentrations in there because it's easier to work with than molarities, because the molarities are going to be so low, your molar absorptivity would be in the tens of thousands. Okay. So how do we calculate this back and forth? If I have a percent transmittance of 50.1, what absorbance would I report? And of course, this is all done for you normally. The equation we use is absorbance is equal to the log of 100, which is 2, minus the log of the percent transmittance. And so in this particular case, that's going to be 2 minus the log, or the base 10 log of 50.1. Yeah, make sure you use base 10 log here, not logarithms, or excuse me, not natural logs. What do we get for an absorbance? 0.3. Let's go. The 2 doesn't affect sig figs here, so let's go 3 sig figs.
0, 0.
Okay. Okay, we can go the other way as well. We can say I have a 1 centimeter cell, and that's what B is. It's path length. And we often leave out path length from Beer's law because we don't change it when we do Beer's law study. But we can figure out what the molar absorptivity of a compound here is. Let's skip that. Again, you could calculate the absorptivity in reciprocal parts per million if you want to, simply by dividing the concentration by the absorbance. Or excuse me, the absorbance by the concentration. Okay, why do we use absorbance versus percent transmittance? If I take data, this is for nickel 2, and I plot percent transmittance versus wavelength. Low percent T means that's where the solution absorbs the strongest. If I change that data to absorbance, I get this. Now, for some strange reason, infrared spectra, come on, are reported this way: percent transmittance versus wave number instead of wavelength. Same idea, though. And so your peaks go down. But for analytical studies, it's the reverse. Everybody else who does spectroscopy does something like this. Now, why do we do this? Why do organic chemists use percent transmittance? That's always the question, all right? It has to do with Beer's law. If you try to relate percent transmittance to the concentration of an analyte, this is what you get. Is that linear? No. Take the same data, translate it into absorbance, now it's linear. So, what is Beer's law? What does this tell us? It tells us that absorbance is directly proportional to the concentration of my analyte, whether it be in terms of moles per liter or parts per million. It doesn't matter. Okay? What K really is, it's either absorptivity times path length or molar absorptivity times path length. But for our intents and purposes, leave it as one component because you're not going to change the path length no matter what you do. Okay, we don't mess with things like that. The only time we messed with it was in the copper, or using those copper solutions, because we found that the longer path length gave us absorbances that were too high. Now that leads to another issue that we have to discuss. This. One of the things I said earlier is if you want to do good analytical studies, you want to have solutions that have absorbance values of less than 1. Now let's see why this is. If, come on, now this pen just crapped out. See if I got another one that works. If the absorbance for a solution is 2.0, what's the percent transmittance? What is it? How do we figure this out from this equation? What are we going to do here? We can say this. Let's add log percent T to both sides, and let's subtract absorbance from both sides. So if we do that, we get log percent T is equal to 2 minus A. Okay, now how do we get rid of that log term? Yeah. So my percent transmittance is going to be 10 raised to the 2 minus A power. So in this particular case, what does that mean? Percent T is going to be 10 raised to the 2 minus 2 power, or 10 to the 0 power, which is 1. Okay, so that's really low. So essentially, if I have a solution that has an absorbance of 2, it's letting through 1% of the light that my blank is letting through. That's what this is saying. Now, what if absorbance is 1? Yeah. Now percent t is going to be 10 raised to the 2 minus 1 power, which is 10. So that jump in 1 absorbance units represents 9% transmittance, whereas the jump from 0 to 1 represents 90% transmittance. So here's what you want to think about. If absorbance is 2, you're letting through 1% of the light you're letting through your blank. If absorbance is higher than 2, that percentage gets even lower. How accurate is that going to be? It's not going to be very accurate. You're exceeding the limits of your detector by doing this. So typically what you want to try to do when you're doing absorbance studies, and this is true both for the atomic absorption, because you are doing absorbance studies there, as well as UV visible spectrophotometry, is you want to make sure that the solutions you have are ranged, say, from absorbance from 0 to 0.7. Somewhere in that range. 1 at the absolute outside. Because you want to think about this is a logarithmic scale as well. The higher the percent, or excuse me, the lower the percent transmittance value, the absorbance is going to jump up logarithmically at that point. We calculated before, 50% transmittance has an absorbance of 0.3. That's half as much light that's getting to the detector versus your blank. So from 0 to 50, you're going from 0 to 50%, or excuse me, from 50 to 100% transmittance, you're going from absorbance 0.3 to absorbance 0. So that's the best range because you're going to get the biggest variation in absorbance across that range. All right, so if you ever deal with this, and actually I had a student that had this problem last semester, and he didn't consult with me, and so his data got all screwed up. He was doing an independent project on hops, alpha acid and hops, and he followed a protocol, but the solutions he made had absorbances that had a value of 4. And he tried, and he said to me, my results are screwed up, but he didn't say why. And so when I went back and looked at his data, there's your problem. Your absorbances are way too high. Your instrument response is no good, so your data is going to be all over the place. You had to dilute the solutions down so that those absorbances were lower. So if you have a solution with absorbance of 4, what would you do? By what factor would be a good factor to dilute it by? That's too much. How about 10? Go from, if you do a 10-fold dilution, you've got a solution with absorbance of 4. You do 10-fold, now it's going to be 0.4. That's very reasonable. That's about 55% transmittance or so. That's good. So that's one of the things you have to think about with regard to Beer's law. Okay. All right. I think I'm going to stop there. We're going to pick up with some problems in this, and then we'll move into electrochemistry. Of course, that's going to be after the exam. So that's in 2 weeks from today. So remember, next week you do have your first exam. It's going to cover the first unit of the course. Handling numbers, statistics, equilibria, titrations. Okay, if you want some guidance about the kinds of questions I'm going to ask on the exam, the best place to look is in your notes. Okay, I'm going to ask you questions of similar nature to the kinds of things that we covered in class.
Going over the book problems also help?
Yeah. Okay, and you've got recordings for all that stuff as well. All right, so if you're looking at a word problem, you run into a blank because there's a hole in your notes or something like that, go onto Canvas and find the class, and you can kind of scroll through the YouTube video to the point where I go over that specific problem, and then